You good?
How is the job hunting process going for you?
Uh, been interviewing, but nothing yet.
Mhm. What roles are you looking for?
Product data scientist mostly.
Mhm.
What about you?
Yeah, so also like either like product data science or like decision data science or research data science.
All right, Charles. I've made you host, so you're free to start whenever you're ready.
Okay.
Hi, guys.
Hi. I will drop the link to the Dropbox in the chat. I will be working out of a notebook titled Code Challenge 3.1.22. So I'll just give everyone a minute to download the contents and open up the notebook, get your environment ready.
Hey Charles, when I click the link, it's prompting me to like make an account to access the folder.
Oh, sorry. Let me share the public link. I probably just shared mine. All right, this one. 1 second. That link should be the public link.
Yep, that one works. Thanks.
All right, cool.
Which document are we working on?
It's a Code Challenge 3.1.22.
Okay, got it. Thanks.
Hello, Catherine. If you're just joining, there's a link in the Dropbox. You can follow the most recent one there's a link in the chat to a Dropbox folder where it has the content for today's lecture. We'll be working out of a notebook titled Code Challenge 3.1.22. Just let me know if you have any issues setting it up.
Okay, thank you.
Is everyone set, or do we need another minute?
Sorry, could I just have 1 minute? I'm just downloading
Wait.
it.
No problem. Joe, if you just joined, we're working out of, if you go into the chat, the most recent link, if you follow that Dropbox link and download the contents, we're working out of a notebook titled Code Challenge 3.1.22. All right, are we all set? Are we needing a moment? All right, I guess we will get started then. So our first challenge for today is we're going to look at the prime triples problem. So the problem is stated as follows. We're going to look at all the set of 4-digit primes. And it turns out that there are 2 triples of primes such that the digits of the primes are permutations of each other, and the primes in increasing order are an arithmetic sequence. So for an example, we see we had this triplet here, 2969, 6299, and 9629. Obviously the digits are permutations of each other. And if we did the math, we'll see that this sequence actually is an arithmetic sequence, meaning that the difference between each successive element is constant. So whatever 6299 minus 2969 is, that same value is equal to 9629 minus 6299. So that's what it means to be arithmetic is you start with some number and you add a constant to it, and your next number you add the same constant, and you generate a sequence that way. So all constants are equidistant from each other. All elements of the sequence are equidistant from each other. So what we're gonna do is we're gonna write a Python program to find the other triple. There are 2, so 2969, 6299, and 9629 is 1. We wanna find the other one. Our implementation will find these triples immediately. The program is not gonna take long to run at all. And we're gonna sort of break this problem down piece by piece. So below here are some functions that I personally used. You don't necessarily need to use them in your process. This just sort of like was my some of the functions I used to solve the problem. And as a hint, we may find itertools useful at some point, and you may find default dictionaries useful at some point. So what would be the first step of this problem? Or if anyone wants to shoot out any ideas of how to go about solving this problem or some first thoughts. Okay, well, the first step I think is what we want to do is we're asked a number about 4-digit primes, right? So the first thing is to actually either write a function that can identify these prime, write a function that we can write a predicate function to identify prime numbers, a function that returns true or false whether a number is prime, or we can write a function that sort of just generates these numbers. So our first step is to write some sort of function to identify or to aggregate the 4-digit prime numbers. So that should be step 1, is like we want to get these numbers so that we can actually do something with them. So your prime function finder or prime function predicate doesn't need to be anything sophisticated. That's not where the speed of the problem comes from. The speed will come from something later down the road we use. So our first objective is to write a function that either identifies a prime number or given some interval will generate all the prime numbers within that interval. Either or is fine. Both can be used for a solution. I personally just define this function that just generates all the primes, but you can do it either way. So that'll be the first step, is to actually just get the list of primes that we want to consider. So I'm gonna say, let's say, what time is it? It's 10:10. I'm gonna let everyone work and make some breakout rooms, and at 10:20 we'll reconvene to talk about how we found the primes and everyone's approach. Are there any questions on what we're doing for this first step? All right, if not, we will reconvene at 10:20. Oh, sorry. Okay, we will reconvene at 10:20 and we'll share our solutions for how we generated the primes. And if anyone has any questions, feel free to reach out. All right, everyone's back. Does anyone want to share a solution, approach, partial solution, or a thought process for finding primes or determining whether or not a number is prime?
So I Googled it. I mean, I don't know whether interview can do that, but if all the numbers in the int adds up divided by 3, then it's a prime. It cannot be divided by 3. It's a prime.
So your condition for checking whether a number is prime is checking whether or not it's divisible by 3?
Yeah, it's like
Or check-
3. Take all the letters. Take all the integers in the number, and then adds up. Calculate the sum is divided by 3 or not.
Oh, I didn't realize that was true. I certainly didn't consider that or think of that. If it works, it works. So you said you have a number like, what is the number that's prime? 17. So you sum the digits, you get 8, and since 8 is not divisible by 3, it's a prime.
Yeah.
Okay. I was not aware of that fact. I didn't know that. That's a really cool hacky way to do it, actually. Okay, if it works, it works. I didn't approach it like that. But I'm just gonna use the approach, one of the approaches that I have, just so I don't like break my code or anything, just for the sake of the presentation. But I mean, that's one way to do it. Does anyone have a different way, a less hacky, more iterative way of finding a prime?
Or maybe divided by 2 and then divided by 3. I don't know how much I need to loop though. I wasn't sure.
Oh, for this approach?
No, just divided the number itself, not like
just in
adding them
general.
together. But
Okay,
divided,
yeah.
So that's a loop I saw.
Yeah, so that's one way to do it. So the way that Tom is talking about is what we can do is if we want to just check whether a number is prime or not, then what we do is just say, well, given some number, we know, first of all, we know if it's divisible by 2, then it can't be a prime, right? So the first we can check and we say, well, if x modulo 2 is equal, come on, is equal to 0, well, then we know that this thing cannot be a prime, right? Return false. Don't need that. All right, otherwise, so we've gotten rid of every even number, right? By checking for 2. So now we just want to check if it has any odd composites. So the way we can do that is for another for loop. So we're gonna say for I in range, we just need to check 3 because we already checked 2, 3, 2, and this is a little not very important detail, but we actually don't need to check up to x. We only need to check up to the square root of x, because it's not possible for a number to have a composite number that's larger than the square root of that number. So what I'm going to say is int math dot square root of x. Let's go +1 just in case. I think that should work. And we want to go to steps of 2, right? We want to check, since we already checked modulo 2, we know we've taken care of any number that has a composite even. So now we want to check whether the number is divisible by 3, 5, 7, 9, 11, 13, on and on and on. So that's what this for loop is going to do, right? And what do we want to say? We want to say if x modulo I is equal to 0, then we know it's not prime, right? We know the number has a composite number, then we're going to return false. Otherwise, we've gone through all the checks. We know that there's no even composite number of x. We know there's no odd composite number of x if we get to this point over here. So then the last thing we want to do is we just want to return true. All right, and this should work. We can just do a check. We can just, for sanity, we can say, let's just say x for x in range 2 to 20 if is prime of x. Ooh, name math is not defined. Okay, let's import math. Three, 5, 7, 11, 13, 19, 17, 19 seems to work. Let's just go a little higher, make sure. Sanity check. Okay, 19, 23, 29. Let's go to 60. 3, 5, 7, 11, 13, 17, 19, 23, 29. Yep. All right, so this seems to work. Does anyone have a different approach? Okay, I just want to sort of put this on you guys' plate to sort of consider. There's an algorithm called like the Civ of Eritranos, or some Greek type name like that. It's called the Civ of Eritranos. And the algorithm is sort of as follows: is you have this list of numbers. So we have, let's just do numbers 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What we do is start at 2. And we take this value of 2, and well, we know 2 is a prime, right? So we're going to keep it. But what we do is we go through a loop and we add 2 every time we go through a loop to sort of knock out every multiple of 2, if that makes sense. So what we do is we start 2, and then we look 2 down. So we go to 4, and we know that since we got to 4 by some multiple of 2, we know that 4 can't possibly be prime. So we get rid of this guy. And then from 4, we go to 6, we add 2. And we knock out 6 because we know it's a multiple of 2. And from 6, we go to 8. And we knock out 8 because we know we got there by some multiple of 2. And then we go to 10. And we knock this guy out. We know none of these numbers can be prime because they were all gotten to by a multiple of 2. So what we have now is we have 1, 2, 3, 5, 7, 9. So the next step in the algorithm is we go over to the next number that we haven't knocked out. That's this 3. And what we do here is now we try to get rid of every multiple of 3. So instead of adding 2, now what we do to get rid of this is we add 3. We knock out every number that's a multiple of 3. So we go over from 3, and we go to 6. We already knocked it out, so that's fine. And from 6, we go to 9, and we knock it out because we know we got to it by some multiple of 3. All right, so we go 1, 2, 3. So the next step in the algorithm is to go to the next non-knocked out number, which is 5. Here, and we knock out every multiple of 5. So we just go from 5, we add 5 to it, and we knock out 10. It's already knocked out. And we just keep on going down the list. We go to 6, we don't have any multiples. We go to 7, we don't have any multiples in this range. So at the end of the algorithm, what we're left with is, well, barring 1, we have 2, 3, 5, and 7 as the prime numbers found by our Civ of Eritranos, or whatever the name is. So I'll just quickly show you guys the code for that. I won't type it out, just copy and paste my solution just for the sake of time. But it's just something sort of mull over and to be aware of that this algorithm does exist. So this primes, let me actually just, let me just copy the whole thing over. I don't want to make a mistake. So what we do is this find primes. We have a lower bound and an upper bound. For whatever reason, I named it H. And what we do first is, like before I said, we make our candidates. So if we want to consider all primes within some lower and upper, or low and high bound, we make a list of all possible candidates, right? And then what we do is for every candidate, we say if the candidate has already been knocked out, we knock out something by setting its value to 0. Then we just continue. We've already knocked this thing out. Otherwise, we have this variable called t, and we say it's 2 times I, and we say while t is less than the length of the candidates of the numbers we can consider to be prime, we set candidates to t equal to 0, right? That's what we did before. Is we looked at the 2, we got rid of every multiple of 2, and then we add 2 onto t. So then we go to 4, knock it out. Go to 6, knock it out. And if we get when I is 3, we start with t is equal to 6. We knock 6 out. Then we add 3 onto it, knock 9 out, add 3 to it, knock 12 out, and so on and so on. So once this loop terminates, what we're left with is candidates. The only thing in candidates that is non-zero are the primes themselves. So all we do is we return every element in candidate such that E is greater than the lower bound. We're only interested in things greater than the lower bound, right? So we run this function. We run def find primes. It should do very similar thing to this. So find primes from 2 to 60. Hopefully this works. Okay, yeah. So mine's just actually included. So 2. So 2 should be a prime. So that's an issue with our thing before, but it is find primes. It finds all the primes 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, all the primes up to 60, just like the one above did. And we can actually fix this prime over here. We say, well, if x equals 2, right? This is like sort of like an edge case. 2 is the only even prime number. Then we want to say return true. It's a really quick fix. So now if we run this, we should have results that entirely match each other. All right, so that's a few ways of finding primes. So we just did the old-fashioned way of just sort of checking whether or not a number is composite using this is prime predicate. And over here we have, it's called like the Civ of Eritranos, something like that. And it's an algorithm for finding prime numbers within some range. Okay. So now we have these numbers, right? So remember the original problem was we want to look at all 4-digit primes. So given these two functions, how are we going to generate all 4-digit primes? Well, we can just use our find primes function, right? So we just say find primes, and we just want all 4-digit numbers, right? So let's just say, let's find primes. We'll start with 1,000. That's the first 4-digit number, and it's going to go up to 10,000. That's the number right after the last 4-digit number, right? That's 9999, then 10,000. 10,000 will be included because it's not prime. So that's fine. So what this is going to do is going to generate all the primes, all the 4-digit primes. So we see every number in this list. It's 4-digit and it's prime. So I have to take my word for that. I'm not checking all these, but yeah. How else can we do this using our other function? So right here, all we can say, we just say our range, right? We just change this to 1,000. and make this 10,000. That's 10,000 here. And it's going to do the same exact thing. Got two identical lists. So for one, we use a sieve. The other, we use just our is prime predicate to sort of filter out the primes. So that's the first part of the problem. Is now we actually have, we can generate all 4-digit primes. So if we go back to the problem statement, let's just reread it to refresh ourselves what we actually want to do. So we found all 4-digit primes, and we want to find a triplet such that the digits of the primes are permutations of each other, and the primes in increasing order are an arithmetic sequence. So the next thing we want to check, we want to do is we want to organize these primes. We want to group them into primes that are permutations of each other. Right. So for example, these aren't prime numbers, but if we have the numbers, 1, 2, 3, 3, 2, 1, 4, 5, 6, 6, 5, 4. Our next step is to write a function that would take this list and somehow group together the numbers that are whose digits are permutations of each other. So we want to write a function that would group together 1, 2, 3, and 3, 2, 1. These guys get grouped together. And then the function should also group together 4, 5, 6, and 6, 5, 4. And the way we're going to do this is we're actually going to store these groupings into a dictionary. The trick to this is to consider a dictionary needs a key and a value. And I'm telling you that the value of our dictionary is going to be a list that's going to contain all 4-digit primes that are permutations, whose digits are permutations of each other. The only thing that we sort of need to consider and think about, and I don't want to give it away, is what is the key for this dictionary going to be? How do we uniquely identify all the 4-digit primes whose permutations are, whose digits are permutations of each other? That's something that we're going to think about for a little bit. So this next step is what we want to make. We want to make a grouping. We want to generate this dictionary that groups together of all these primes, 4-digit primes that we generated. We want to create a dictionary that groups together all the numbers that are permutations of each other. So that's the next step. And the trick here, something to consider and think about as you're doing this next step of the problem, is how do we uniquely identify the list of 4-digit primes that we can use as a key to access the list of the 4-digit primes in our dictionary. So are there any questions on this next step of the problem? Okay, if not, I think we'll take, I'll give a little bit more time for this one. I think we'll take 15 minutes to consider this. It's a little trickier than just actually generating the primes. So at 10:50, we're going to reconvene to discuss the solutions, partial solutions, thought processes of this next step of the problem. And if anyone has any questions in the meanwhile, just speak up. I'll make the breakout rooms again, and I'll jump from breakout room to breakout room to make sure that everyone's on the same page. So if there are no questions, we'll reconvene at 10:50 to discuss solutions. All right, welcome back, everyone. Does anyone have a solution, partial solution that they'd like to share? Or any thoughts?
I was wonder maybe find out all the numbers and then make sure the numbers are from small to large, and that would be the key. And then the others are you divided others by 6 and then see whether it's one left. Where's
So this is
one
gonna
or minus
generate-
one?
This is for the generate permutations function, right?
Hmm?
Okay. So what would your key be? What would
Sorry?
your key be? What you said that your key would be something, I just didn't quite catch it. What would your key be?
Oh, actually, let's put this way. You can calculate, you already find that list, and you can calculate all of those, their sum of all the digits. If they are the same. Oh, okay.
Ooh, that's not quite, right? You see the fault in logic there? Right? Because we could have like a number like 1, 2, 3, or like 1, 1, 4. They would sum to the same, but they're not permutations of each other.
Yeah, their
So that's
sum
not-
of the digits are the same.
Yeah, but they're not permutations of each other. So we use that.
Yeah,
as the
they're
key.
not permutation.
It's not going to group together the permutations. It's just going to group together all the numbers whose digits sum to the same number. So
I cannot hear you very clearly, sorry.
Oh, sorry.
Maybe,
anyone else
maybe
have-
it's me.
Does anyone else have an issue hearing me? No one else is saying anything in the chat, so I'm not
Okay.
sure if it's on my end or your end. But is
It's
it any
probably on
better
my
now?
end, sorry.
Yeah, you're good, Charles.
Okay. Sorry about not being able to hear me clearly, but hopefully this here. So the idea is if you have a digits, like imagine you have digits like, hopefully you can see this, 1. Right, imagine we're given these 3 digits, like 1, 2, 3, 3, 2, 1, and 2, 1, 3. We want to find a way to generate a key that's going to be unique and unique to only these digits, right? So the idea is we want to take, these numbers. The idea is to take the digits of these numbers and sort them, right? That's going to generate a unique key for all permutations, for all numbers that have the same permutation, right? Or for all numbers whose digits are permutations of each other, right? For this one, this would be a key. The key would be 1, 2, 3, right?
Yeah,
Because we sort the digits, and then this is gonna this key is gonna uniquely identify all these numbers, right? Because they're all have the digits 3, 2, 1 just in some order, right? So this is the way we're going to generate our key to store our values. And we're going to see that in code shortly, unless someone else has some code or some line of thought or any questioning before we proceed. Okay. Well, if not, we will write out the code. Sorry, what was that, Adar?
Oh, I was just asking, so you're not getting other permutations like 2, 3, 1, 1, 3, 2. Like there's like certain
this is just an
permutations.
example. Those are an example. I didn't include all of them, but imagine next we look at a number 1, 3, 2. Like it comes in.
Okay.
Right?
And
we want to know where to, we want to know where to put it, right? So from this, we can generate its key, and its key is going to be 1, 2, 3, because we just take the digits and we just sort them, and then we know exactly where in the dictionary to put them because we generated the unique key for it.
Got it.
And the same thing for whatever, anything else I didn't write, like 3, 3, 1, 2, right? 3, 1, 2 comes in. Where do we put it? We just take the digits, sort them, and that's our key. And then we know exactly where to put it. And we'll see that in code right now. So what we're going to do is we're going to make our dictionary. I'm just going to call it dictionary. And I'm just going to use a default dict for convenience. And what this does is it creates a dictionary. And what it does is it says, if I try to query a key in the dictionary that doesn't exist, default dictionary will create that key and put as its default value an empty list. So if I say D and I want to get like, D of 1, D is empty right now. So if I say D of 1 with a regular dictionary, it would throw a key exception error or something like that. But with default dictionary, it's smart and it handles it for you. So it creates this key, it creates the value as an empty list, so you don't get this error. It's just a convenient way. It saves you from writing code. But this default dictionary acts the same exact way as a dictionary. It's just sort of saves you from writing this extra code of checking what are the keys in the dictionary before querying it and all that nonsense. So it's just a little less code for us to write on our end. So, right, we're given some list of primes. I don't want to type that over. Right, our generate permutation dictionary, we have this primes, which we know is going to be the list of all primes that are 4 digits long. So what we're going to do is we're going to say for prime in primes. We want to put it into our dictionary. We want to store it somewhere. So I'm going to do this. I'm going to say, this is a function that we haven't written it yet, but I'm going to say D of generate key of prime dot append prime. And return D. So what this code is doing is we haven't written this generate keys function yet. I'm actually going to just define it up here. Generate key of some value X. But what we're doing here is we said, we have a list of primes. We made this empty dictionary. And for every prime, we want to figure out where to put it. We want to group the permutations together, right? So what we're going to do is for every prime, we're going to generate its unique key so we know where to put it, right? Because like we said before, when 1, 2, 3 comes in, where do we put it? Well, when 3, 2, 1 comes in, where do we put it? Well, we generate its key, which turns out to be 1, 2, 3. We take the digits and we order it, and we append it into 1, 2, 3. So let's say we have entry 1, 2, 3 here. It's some list. Then we know to put 3, 2, 1 in it, right? And then what happens when 2, 3, 1 comes? We do the same thing. Is we generate its key by ordering its digits. We order its digits. We get 1, 2, 3, and we know to put it into here. Now, what happens when something like 4, 5, 6 comes through? Well, 5, 4, 6. What do we do? We generate its key. So we generate its key by looking at all the digits, putting them in order, and that's going to be unique for this permutation, right? So when we take 5, 4, 6, we're going to get the key 4, 5, 6. It's going to go in, and what we're going to do is we're going to put the number 5, 4, 6 there. And that's how this process is going to work. Is for every prime, we generate its key, and we plop it into the list that has all the permutations we pop into the list where the rest of the numbers that have the same digits live. So how do we generate this key? What we want to do is we want to first take a number. For example, we'll take a number like whatever, 3, 2, 3, 1, and we want to pull every digit. So does anyone have any idea how to do that? We want to get a list of its digits from a number.
Can you turn it into string and then split?
Yes, you can do that. That's a hacky way to do it. So what Hadar said was you take 2, 3, 1. And then what you do is like you split so that you get something like this. You get 2, 3, 1. That's what split will give you, is this list of 2, 3, 1. And then what you can do is just go over every element and convert it to be an int, 2, 3, 1. That's one way to do it. That's a bit of a hacky way to do it, and that's totally fine. But I also want to, this is totally work it, but we'll write this out in code just so we can see. So we'll write this generate key, we'll call it 1. We'll write a few. But so Hadar's thing was to say, we'll say x as string is just going to be equal to string of x. We just cast it to be a string. And then we're going to say list of, let's call it nums. We'll say nums is going to be equal to x as string dot split. And I think it's no argument. It will just split every character. And then we want to say nums is going to be equal to, we're just going to iterate over and say int of num for num in nums. Then we're going to return nums. Well, we're not going to return nums yet. So this, what it does is it actually gets us a list. We'll just, let's just print nums now to make sure this actually works. So let's see if we do generate key of number 1, 2, 3.
Key
And
one.
generate key.
Generate
yes,
key
yes.
one.
Yes. Oh, didn't split it. What do we have to split on? Well, that's what we do it for.
I think maybe, is it just split x's string? I forget how. Yeah.
Yeah, I forget how to do this. We'll just split string into a list of characters. When in doubt, just, oh, there's a split function. So we just write, split of, yeah, that word. Okay, you were right, yeah. So we want to do, we can just say split x as string. Rerun it. Oh, what's the issue? Name split is not defined. Oh, they had this function defined here. Okay, we'll just copy this over.
Oh, wait.
There should be an easier way to do this.
No,
but
yeah, there's definitely a built-in split function.
yeah.
Yeah, that's weird.
Oh, it looks like we call list. Oh, nice. We just called, okay. All right, learn something new every day. It looks like what we can do is just say list x as string. Okay, there we go. So we cast this to a string. We take the nums, we turn it into a list. So the string 1, 2, 3 now becomes the list of characters 1, 2, and 3. Then what we do is just cast it back to an integer for num and nums, and then we just print it to make sure it actually did what we thought. So we're close, but now if we do 3, 2, 1, right? We get 3, 2, 1, whatever. But remember, we want to order these so that it's unique, right? So that every time because if we split whatever 104, that's going to generate the key. Right now we generate this list 104, right? But if we split 401, the key is now 401. These are different keys, but we want them to be the same keys. So we make them be the same by sorting the digits. And if we sort the digits, then these are going to be the same. 104 is going to go to 014, and 401 is going to also go to 014. Oh, yeah. All right. So
And did you say there was another way to get the into a list format?
Yeah, we can go over that in a second, but I just want to flesh out the rest of your
Oh,
idea.
okay, gotcha. Sorry.
Yeah. So the next thing to do is what we're going to do is we're going to say we want to sort this, right? So what we're going to do, we're going to say nums is now going to equal to sorted of nums. So now if we just print nums, let's see what happens. Okay, so now it takes 3, 2, 1, turns into key 1, 2, 3. Take 2, 1, 3, key 1, 2, 3. So this is really what we want, right? And of course, 1, 2, 3 should go to there. So now we take any permutation of digits gets mapped to the same number. So this is great. Our key is looking nice. The only last thing is when you have a key in a dictionary, it can't be a mutable type, because if you had keys as mutable types, then later on I can change the content of that key. If it's a list, I can append to it. And then I've broken the data structure because I've changed the key. So now if I access the key, it may not be in the dictionary and I've lost all the data associated with that key. So whenever you have a key in a dictionary, it needs to be an immutable type. So what's a quick fix to make this immutable?
Isn't it how, if you add like the underscores to the name of it, well, that indicates immutability.
That's the general practice of what you do to name a variable that's going to be private.
Oh, right. Okay.
Yeah. To make this immutable, it's a list. All we do is throw in a tuple. Tuples are immutable in Python. So we literally just throw this list sorted of nums returns a list, and then we just throw it into a tuple. So now if we print nums, we get a tuple. The brackets have turned to the parentheses, which indicates it's a tuple. Anyways, so okay, so now we can generate, we have our key. We have an immutable key that can map any permutation of digits to the same number, right? So I'll just quickly show you the way that I had. It's, I don't know if it's better or not, but it's just a different way to do it. So for me, what I did was I said, I made an empty list called digits. And I said, while num, and what this is saying is while number is not equal to 0. That's what this is short for. This while num, as long as this number is not equal to 0, this is going to keep on going. What I'm going to do, I'm going to say the number and the digit is going to be equal to div mod num 10. What div mod does is it returns the floor division and the module as a tuple. So the floor division is going to be number. So a number like 120, when I divide by 10, the first argument is going to return as 12. And the last is going to be the remainder. So it would be a 0. So that's how we're going to split out every digit. So what happens if we have a number like, what div mod is going to do for a number like 1, 2, 3 is I take it and I divide it by 10. I div mod this number. I'll just call it DM for short. What it returns is this number divided by 10 as one of the arguments. So that's going to be the floor division of this number. So 1, 2, 3 divided by 10, we're going to get 12 as the floor division. And then the second thing it returns is the remainder. So when we take 1, 2, 3 and divide by 10, the remainder we get is 3, right? So what we've gotten here is we now have the last digit and we have the floor division. So now what we do is when we do div mod of 12 and 10, what we get is 1 and 2. And when we do div mod of 1, we just get 0 and 1. So what we've done is we've pulled out every digit. We've pulled out every digit from there. So that's what this code is going to do. So while num d is going to be div mod d, I'm going to just digits dot append d. And then all I'm going to do is just return, again, we're going to make a tuple of the sorted digits. And that's how I did it. I don't know which way, I'm sure there's an argument for either that can be made for which one is better or not. This way is certainly less hacky. As for efficiency, I think we're only dealing with 4-digit numbers, so there's no really penalty for efficiency for such small cases, but both work. So yeah, so what we've done now is we've just created the function to generate the key, right? So now our generate permutations dictionary function is done. What we do is, well, first we'll make a list. We'll say primes is going to be equal to, what do I even call the function? Find primes between 1,000 and 10,000, right? That's going to make our primes. And then what we're going to do is we're going to say dictionary is going to be equal to generate. Oh, there we go. Nice. Autocomplete permutation dictionary primes.
You're missing a D on your append. Yeah. For your generate key. So digits.append and then
Thank you. Yeah. And then I'm also gonna have to import default dict. So down here, I'll just import. It is from collections or default. And that's all I didn't spell anything wrong. Local variable num reference before assignment. All right, now what? Oh, I called it X. Whoops, I'll just change this to num. I just have the name draw. All right, there we go. Okay, so now we should be able to look at D. Very cool. So these are all, so now if we take a look at this dictionary, it's done exactly what we wanted. We've grouped together the permutations. That was the whole purpose of this part of the problem. Was we have now, through a process of generating a key for every prime, such that every key maps to the permutations of that key, we see that all the primes 1601, 1601, 6011, 6101, these are all prime numbers and they're obviously all permutations of each other. So we've solved part 2 of the problem. The next part of the problem is we want to go through every single grouping we have, and we want to see whether or not there's a why am I blanking on the word for it? A arithmetic sequence within that group. So that's the third part of the problem is we have this dictionary, it exists. We want to go through every value in the dictionary, which every list of prime 4-digit primes that are permutations of each other, and we want to see whether an arithmetic sequence in there exists. And at this point, for this next part of the problem, which we'll probably work on for another 10 minutes, this is where, if you look at the combinations, where is it from? From itertools, if you import combinations, that might be a useful function. So if you look at the documentation for combinations from the itertools package, that might be useful in some way for this part of the problem. So this next part, what we want to do is, actually we'll take a mini part. Well, we want to define this is arithmetic. So given some sequence, like, you know, whatever, 1, 2, 3, 4, or whatever, 5, 3, 1, -1, we want to write a function that determines whether or not it's arithmetic. So this is like the first small part. We'll say we want to define this function is going to help determine whether a sequence is arithmetic. Then we want to iterate over every value in the dictionary and apply this function to every possible 3 combinations of every value in that dictionary to see if we can find a permutation, a arithmetic sequence of permutations in that dictionary. Are there any questions on what's the next steps?
Nope.
Okay, if there's no questions, I'll set the breakout room. What we want to do is we want to define is arithmetic, and we want to iterate over the dictionary using its arithmetic to see if we can't find some sequences. And also from itertools, combinations may be useful in this part. We will reconvene in, you know what, let's take a 5-minute break. So let's say at 11:17, we'll reconvene. And then from 11:17 to 11:30, we will discuss our solution. So feel free to do whatever you gotta do for the next 5 minutes. And then we'll take the 15 minutes after that to work on the problem. And we'll meet after that to discuss the solutions. I will create the breakout rooms now, but feel free to take a break.
Hey Charles, so for arithmetic, is that like if they have a common factor or if they have a difference between each number?
Oh, sorry. Yeah. So an arithmetic sequence, we talked about this before you logged in, but if you, an arithmetic
Oh,
sequence
yeah.
is a sequence of numbers whose difference between each successive term is constant. So like sequence like 1, 2, 3, 4 is arithmetic because the difference between every term is 1. Different like 5, 3, 1, -1 is arithmetic because the difference between every term is -2. But a
So would
sequence
1,
like
2, 4, 8 not be arithmetic?
no, that's geometric. That's a geometric sequence is where
Okay.
every number is a multiple of the prior number.
Got
This
it.
is additive. Yeah,
Okay, cool. Thanks.
no problem. All right, welcome back, everyone. Does anyone want to share their solution, partial thoughts, thought process, partial solutions to defining the is arithmetic function? All right, in the chat we have this function.
I am not sure. I tried to run it and it works, but I'm not sure if this is because I didn't use the what's that? The iter tools.
Oh, I see. So you don't need it, but I see you're referencing the dictionary here. I don't think we don't want to reference the dictionary because when you reference a dictionary, S of key is a list. So what you're taking here is the difference of two lists. So this might work in your code because you have your dictionary S defined, but we don't have S defined over here. So I wouldn't be able to run this code and have it actually run. But what we want to take as a sequence is some list of elements and return whether or not it's arithmetic. But I see your logic is probably straightforward. Like, so you find the difference of the first two elements. And all I want to say is, for every analogously element in my list, I want to make sure every successive element, it matches. And that's entirely the correct logic. But I just won't be able to run this code over here because I don't have S defined, and also you're doing it through the dictionary. But just for the sake of just being consistent with my code in the notebook, I'm gonna just transfer your logic over to operating on a list. So just like, I'm sorry, Joe, just like Joe's code said, for is arithmetic, what we want to do is we want to look at the differences of every successive element, because that's sort of the definition of an arithmetic sequence, is that every sequence's difference is the same. Or we take some element, we add some constant to it to generate the next term, add the same constant to generate the third term, and so on and so on and so on. So all the differences should be constant. So what you do is first is we're going to just generate a differences list. So I'm going to say differences is just going to be equal to, and I'm just going to name this, call this sequence L, just for the sake of typing. We have some list. What I'm going to use list comprehension to create a list of differences. So what I'm going to do is I'm going to say L of I minus L of I minus 1. It's going to get the difference of every successive element. I'm going to do for I in range 1 to length of L. So what this does is now we have this differences array. So if we take this function and we run it, I'll say is arithmetic of 1, 2, 3. Oh, wait. Oh, it's because this one's defined. Oh, wait, it overwrote it. Just return differences, just so we take a look at what it's doing. Name differences. Name differences.
You have a typo on where you say differences. Yeah. You just need an E between.
Yeah, thanks. All right, so we found the difference. Yeah, a K element list, so we're going to return some K minus 1 elements because we're just looking at the difference between elements. So yeah, 1, 2, 3, 1, 3. If we do 1, 2, 3, 1, 4. All right, so now what we got to do is we got to make sure that every element in this list is the same. So just like Joe did before, what we're going to do is I'm just going to say the first element, the first difference we see, I'll just call it F, is just going to be equal to differences. I hate typing differences. I'm just going to call it diff of 0. Now what we want to do is we want to say, we're going to say for every element in diff, say if this element is not equal to F, we're going to return false, because that means that we found a difference that's not equal to the first difference, meaning our sequence is not arithmetic because it's not the sum of the same consecutive term. It's obviously, if we have two different differences, then it means that some different term was used to generate the next term. So it's not arithmetic, so we return false. Otherwise, if we get through this whole for loop and we've never actually terminated on this condition, it means that every element in our difference functions is the same. So it means that our sequence is arithmetic. So then we just return true. All right, just as a Sanity check, we'll make sure this, okay, false, yeah, because this is not arithmetic. True, nice. True, nice. It seems to work. So now we have all of our helper functions. The last part is just to put it all together. So what we've done is down here is we've generated our primes. We've generated the dictionary of all the permutations of these primes, right? So now what we want to do is we want to look through every grouping we have and see if we can't find a permutation that is arithmetic. So what I'm going to do is I'm going to say, what do I want to say? I want to say for every value in d dot values. This is every list of primes whose digits are permutations of each other. What I'm going to do is I'm going to generate. I'm going to say combos. All the combos is just going to be equal to. We're going to have to import something. So from itertools import combination. Yeah, I think that's right. Combos is going to be equal to. Oh, it's combinations, I think. Is equal to combinations of, we're going to take the value as the list. So we're going to take the first argument is what we want to generate combinations of. And the second argument is the size of the combinations we want to generate. So for us, we're looking for triplets. So we're going to say 3. And this should run, yep, we've defined everything fine. All right. So for every list of permutations, we generate every 3-element combination. So now all we got to do is in that 3-element combination, we just need to check whether or not it's arithmetic, right? And combinations has this nice property that when you take combinations, since combinations is order independent, permutations is order dependent, combinations is order independent, it's nice Python implemented it in such a way such that it preserves the ordering of the elements. So we know that every combo in here is going to be an increasing, sequence. We just need to check whether the sequence is arithmetic or not, right? And that's the statement of the problem is we're looking for increasing arithmetic sequences, right? So this is just a nice benefit of combinations is that we don't need to worry about the order because the order is preserved. It's just the way they implement the combinations. So we have these combos, which we know are going to be already increasing sequences. All we have to do is check whether or not combos is arithmetic. So I'm going to say for every combo and combo, what I want to say is if is arithmetic of combo, then I'm just going to, I want to store everything I find. So I'm just going to make a results variable. I'll say this is results just equal to some empty list. I'm going to say results dot append combo. And all I want to do is I'm just going to return results. I'm just going to print results. So we'll run through the logic one more time. Is we have some empty results thing, some results list, which is going to store all the triplets we find. We generate our prime numbers. We then group them according to their permutations. We group all the prime numbers that are permutations of each other, whose digits are permutations of each other. And then what we do is we look through every grouping. So for every grouping, that's what this line is doing. We're going to generate all 3-element combos you can from this particular group. For every 3-element combo, we just check to see whether it's arithmetic. We don't need to do anything about increasing or decreasing because we know that combos preserves the order. So we know that everything's going to be increasing already, right? So we just say if this thing is arithmetic, then what we do is we want to save this result. We're going to append it to the list, and then we're going to print results. So if everything worked, we've gotten our 2 sequences. We already knew 2969, 6299, and 9629 was our given sort of result as an example. We found the other one, 1487, 4817, and 8147. And you're welcome to do the math to check to make sure whether it actually is arithmetic, but it is. And you can see that these numbers are prime. Well, you can see that they're permutations of each other, and you yourself can check whether or not, if you want to, if these numbers are actually prime, but they are. So this is the problem solution. I really like this problem because it really covers a lot. Is that we just reiterate everything we've done. We've done a lot. Is first we sort of had to write a function to actually even identify the prime. We're not given anything. So we have this Civ method to sort of filter out the prime numbers from a list, or we have this prime predicate, which just checks whether or not a number is prime. We can use either method to generate the primes, doesn't matter. Next, what we did was we had to actually find a way to sort of store these numbers together. So we had to create this dictionary. We had to find a way to store all the permutations together that we wanted. So we had to create this dictionary. We had to use this sort of clever technique to generate a unique key, which is not, straightforward, to actually sort of group these numbers together. And once we've had our dictionary, we then defined our is arithmetic function, which just checks to make sure, given some sequence, it actually is arithmetic. And then finally, we sort of glue all that together. We generate our primes using the function that we defined. We create the dictionary using the dictionary function we defined. For every grouping we have, generate all the possible combinations of that group, check whether that grouping is arithmetic. If it is, we append it, and at the end, we return our results. And this is the function. Are there any questions on anything, any steps that we took to solve this problem? All right, I don't think it would be crazy, I think, for this to actually be asked in an actual interview. The reason I like this problem is because it's like, multifaceted. There's a lot of parts to it. And I think you learn a lot from it. You learn how to generate primes. You learn about default dicts. You sort of play around with combinations. We learn sort of how useful these dictionaries can be in storing like things. So if there's no questions on this problem, we're actually just move on to our probability question for the day. And if you just scroll down a little bit, the question is overlapping squares. So given a square area of 100 by 100 feet, we'll just draw this out. We're given a square area of 100 by 100 feet. We're asked, what is the probability that if you randomly drop two 17 by 17 tiles onto that area, they will be overlapping? And the constraint is the tiles will always land within the 100 by 100 square area. And when they land such that their horizontal and vertical sides are parallel with the horizontal and vertical sides of the 100 by 100 foot square area. All that means is that when I drop a tile, it lands so that its orientation is the same as the big square. We're never gonna land like this. We're always gonna land such that the orientations of the little squares, the 17 by 17, when we drop two, they're always gonna be oriented with the big square. So the question is, what is the probability that you drop two squares in this area, 17 by 17, in this 100 by 100 area? What is the probability that they will overlap? So I think we'll take about, we only have 15 minutes. Let's take 10 minutes to sort of consider the problem, and we'll meet back and we will discuss any solutions or any thought processes that anyone had. I will create the breakout rooms again, and if there's any questions on the problem statement, or if you want any guidance, feel free to put it in the chat or just speak up.
Hey, Charles.
Yep.
Should we ask questions if we're a little bit stuck, or should we just kind of Google it and wait until we're all back?
Oh, you can ask me a question, but we're gonna start reviewing the problem in like 10 seconds.
Okay, no worries then.
Yeah. I just closed the breakout room, so we should be rejoining soon.
Okay, sweet.
Yeah. All right, welcome back, everyone. We only have 10 minutes, so I figure it seems like we might just have just enough time to get through the solution of this problem. Does anyone want to share any thoughts they had on the problem, or any partial solutions or full solutions or anything? Okay, so I guess we'll just start. So we're given two 17 by 17 squares. So first thing we want to sort of talk, this looks a little tiny. I'm gonna just move this over. Hope we can, it's work. So first we need to meet is a sort of formalize like a square, whatever. So if we have a square, I'm going to define a square, whatever, as an XY coordinate, as its bottom left XY coordinate. So if I draw a square here, I'm going to define it as having randomly picked this point down here, right? We're just going to call this X, Y. So what I mean by when I drop a square, what I mean is I pick a random X and a Y, and that's going to be its bottom left coordinate, right? And one of the constraints of the problem was the square always lands inside this 100 range. So this 100 by 100 area. So given that, what is the ranges that my X and Y can take if I define my X and Y to be the bottom left corner? What ranges are, well, sorry, yep.
Wait, are we, in terms of range, is the bottom left corner of the big square like 0 and 0, and then?
Oh yeah, this is gonna be 0, 0, yeah.
Okay, cool. So it can go to like 100, 0, and it can go.
Well, because if I make my X and Y 100, that's outside, because I've defined the square to be the bottom left corner.
Right, okay. So it can go to 83, or yeah.
Yeah, exactly. Yeah. So my X, whatever X I pick, it's gotta be less than, it's gonna be greater than or equal to 0, but it's gotta be less than or equal to 83. Because if it's anything bigger than 83, we know this is side length 17. If it's bigger than 83, then it's gonna go outside the square, which we said that we can't happen. That's one of the constraints of the problem, was that guaranteed to always land inside the square. So we know that our X value is constrained between 0 and 83, as well as our Y value. So I also just write down that 0 is less than or equal to Y is less than or equal to 83. So really what this problem is now is we have some, oh, I shouldn't have erased the whole thing, whatever. We have some X1, Y1, this is defined square 1, right? And we have some other X2, Y2. And what we want to find is what is the probability that these two squares land on each other? So what does that really mean? When do we have an intersection between these squares? When do these squares overlap? That's really what the problem boils down to, sort of formalizing mathematically. And does anyone have any ideas on what inequality needs to hold for these squares to be considered overlapping? We're given x1, y1, x2, y2. For these squares to be overlapping, I'm gonna write over here. I'd say the absolute difference between x1 and x2 has got to be less than or equal to 17. And I'm going to say the absolute end, very important, end, the absolute value of y1 minus y2 has also got to be less than or equal to 17, right? What we need is for x1 and x2 to be within 17 of each other, and our y1 and y to be within 17 of each other, right? Because if we have, let's say we have our first square here, what we need is from here, all I need is the x coordinate of the other square to be within 17 of this x coordinate. So it can be 17 this way, or it can be 17 this way. As long as the x coordinate of the other square is in this range, and the y coordinate of the other square is somewhere within 17 this way or 17 down, then anywhere in this area, as long as we draw that other square, it's going to intersect, right? The other square would be parameterized by an x2, y2. If we draw it here, we have an intersection. If we draw it here, we have an intersection. If we draw it anywhere outside of this area, we do not have an intersection. So the crux of this problem really boils down to realizing how do we formalize an intersection and what inequalities need to hold for this intersection to be true, right? So now we have this intersection. So now the next thing we want to do is we're going to look at, it's called the sample space, the space of all possible values of x1, y1, x2, y2. So I'm going to do actually here, the sample space, as we said before, is not 100 by 100. So if we have some, imagine we have some x1 picked and some x2. This is the x coordinate of the first square we drop. This is the x coordinate of the second square we drop. Really, the sample space is, like we said before, 83 to 83. The sample space we can pick from is really this smaller square here, right? So in a previous problem, we sort of applied the same technique as we look at the sample space. And what we realize is we need to find where in the space, so we can pick some x1 and x2. We want to find where in the sample space is, if we pick some x1 and x2, we want to find where does this inequality hold, right? And we saw from a previous video that if we draw this out, so imagine the x1 I pick is anywhere between 0 and 17. Then that means that x2, here, wait, let me draw this out. It's a little tricky. 17, 17. So imagine I pick x1 to be 0, right? That means that x2 can be anywhere from 0 to 17. If I pick x1 to be 1, that means that x2 can be anywhere from 0 to 18, right? Because it's got to be within 17 on either side. So when we continue out this logic, we find that if we do over here 83, over here is 83. We find that anywhere inside this area, supposed to be straight. Anywhere inside this area, this area is where the probability, this inequality holds. If we pick some x1, x2 random, as long as it's within this area, this inequality holds. Again, because if I pick x1 to be, let's say this is like some point 50, then 17 above and 17 below is whatever value x2 can be. If I pick it to be like some point over here, then again, 17 above and 17 below is anywhere this thing can be. So it turns out that the probability of this inequality holding is really equal to the area of the shaded region divided by the area of the whole region. So what that is really the whole region is just 83 squared, right? So we're going to get the area of the whole region is, so the probability of x1 minus x2 being less than 17 is just going to be equal to, well, the whole area is 83 squared. And this area is just the whole area minus these two triangles, right? So we're going to get 83 minus 17 is, this length is 83 minus 17, and that's 56. Minus 56, and this length is also 56. So we get the area of two triangles. The area of a triangle is 1/2 base times height. So we get 1/2 56 squared plus 1/2 56 squared, which is just 56 squared. So really we get, this area is really just the whole area minus 56 squared. And this is the probability that x1 and x2 are within 17 units of each other. That's what this quantity represents. Now, we said before that for there to be a collision, not only do x1 and x2 need to be within 17 of each other, we need the y1 and y2 of the squares to also be within 17 of each other, right? So the same exact argument holds that we had over here. I just change this label from x1 to y1, and from here, x2 to y2. It's the same exact problem. If we pick some x1 and y1, as long as that point falls within this shaded region, the inequality holds. So all we need to do is, again, the same process is find the area of this shaded region divided by the area of the whole sample space, and that's going to be our probability. So the probability that y1 minus y2 is less than or equal to 17 is equal to the exact same quantity. It's equal to 83 squared minus 56 squared divided by 83 squared, right? So the last part of this problem is we've realized the probability of x1 and x2 being within 17 is this quantity. The probability of y1 and y2 being within 17 units of each other is this quantity. So what we want is the probability of this and the probability of this. So the last thing to notice is that picking an x1 and x2 and a y1 and y2 are disjoint events, right? The y coordinate is not dependent on the x coordinate at all. The x coordinate being picked does not in any way sort of restrict what the y coordinate can be. So these two events are independent. So if two events are independent, we want the probability of these two things. If we have probability of A and probability of B, and they're independent, that's just gonna be equal to the probability of A times the probability of B. So what we get finally is that the probability of intersection is really just going to be equal to this quantity, right? 83 minus 56 all over 83 squared, everything squared. This whole quantity squared, right? Because these quantities are exactly the same. So the probability of x1 and x2 being within 17 and the probability of y1 and y2 being within 17 is our probability of intersection. And that's just equal to these quantities multiplied together. And since they're the same, I just get this quantity squared. And this is your final answer. It's 83 squared minus 56 squared divided by 83 squared. Take that number and square it. And that's the probability that two squares intersect. Are there any questions about the approach to this problem? This is in general, a pretty powerful way of going about solving problems. If you can draw up a sample space, which is what this is, the 0 to 83 square, you draw the sample space and try to find the area where some sort of inequality holds, and you interpret it as a probability. It's in general a pretty, if you can formalize the problem such that it's geometric, you can interpret it geometrically as an area in the sample space. There's a pretty straightforward problem with just finding where this inequality for your probability holds, and then just finding the area of that problem. Oh, sorry, the area where that inequality holds. Sorry,
Can
yep.
you go over again how you get the 56?
Yeah,
The
sure.
number 56.
56, because our whole area is 83. Or sorry, our whole length of this is 83.
Uh-huh.
And this length here is 17.
So
Right,
that
so I
should
just
be
did
66, right?
83 minus 17. Let's do it. Let's see. We get 6, 13. We get 6, 5, 56. I think 83 minus 17 is 56, but I could be wrong.
I think it's 66, right?
83 minus 17 is 66.
Yeah.
Oh my gosh, wait, 7. Yeah, oh my God. Yeah, you're right. Sorry. Yeah, 83 My bad. I knew I could be wrong. You're right. Oh my gosh. Can you believe I'm a math major? I can't. Okay, 66. Okay, but our problem, the generalization is not the same. So we changed anywhere you saw a 56. My bad, everyone. Change it to a 66. Good catch. Good catch. Yeah. So the problem, the whole area is still 83 squared. We just want to minus this length, which is, as Joe said, 66, not 56. But then the whole thing is the same. We just changed that 56 to a 66, and that's the probability of intersection. Thank you for the catch. Any other questions or any other things I did wrong?
I don't know if we have time, but if possible, to break down how it is that the area that you colored in captures the inequality or like holds the inequality. I'm just kind of missed
Sure.
that leap, but
Here, so I'm just gonna actually just for the sake of clarity, I'm gonna erase some of this. If anyone needs to run, because I think, yeah, we've ran over already. If anyone needs to go, thank you for joining. I hope this was informative, but if you want to stick around, I'm gonna just sort of go in a little bit more and just describe exactly how we got that area. Let me see if I can whip this up. All right. So let's just make the numbers smaller, just so I can just deal with it. Let's say we have a 10 by 10 square. Let's say this is our sample space is 10 by 10, and we have a 3 by 3 square, right? Same problem, just making it smaller so I can deal with the numbers. So if we pick x1, if x1 is 0, then what can x2 be for there to be an intersection?
sorry, if x1 is 0,
Yeah, if I said that the x coordinate of the first square is 0, then what values can x2 be such that the x1 and
anything
x2 will be
less than 17.
well,
or 17.
I redefined the problem to be 3, right? Just for smaller numbers, just for sanity.
Oh, okay, so 3.
Yeah, exactly. So we get like I want to say like here is 3. Okay, so now if x1 is 1, what values can x2 be?
Oh, up to 4.
Exactly, yeah. So we get 4. So for here, we get this area. When we go to 1, we get this area. Okay, so now when x1 is 2, what values can, I'm not drawing this very well. Here. So when x1 is 1, we can go here. When x2 is 2, we can go to 4. So when
Okay.
x3 is 3, so you see how this sort of like forms out?
Yeah. So I
When
guess
x3 is-
visually, how is it that, like, what about the times where both of the squares are like in the bottom right corner, for example, or in the top left corner?
Top left corner, so like over here?
Oh, sorry, maybe the mirror is imaged. The
Oh,
image.
top left, like over here.
Oh, yeah. Mm-hmm.
Oh, that's when x1, so that's when, does this top left corner represents that x1 coordinate is 0 and x2's coordinate is 10, right? And the reason that wasn't shaded in was because we can't have an intersection at this point, right? They're not within 3 of each other. They're 10 apart.
Oh, sorry. I actually
So
I have
that's-
a meeting, so I have to go. But thank you so much, Charles.
Okay, yeah, no problem. Hopefully it's a little more
this is
clear.
super
But
helpful.
if you just
Yeah.
search like this problem, you'll find like sort of draw diagrams that are probably
Okay.
much more nicely put out than me.
That
But yeah,
makes
thanks for
sense.
joining.
Yeah. Cool. Thanks, Charles.
No problem. Any other questions from anyone? All right, if not, I will conclude. Thank you for joining. I don't know if Courtney has anything to say or if we just sort of are done. Is Courtney even here? No, Courtney's not here. All right,
Thank you so
well,
much.
well, thank you for joining. Thank you for catching my very, very basic arithmetic
Thank
error.
you so much.
Yeah, no problem. Hopefully it was clear. And then again, thank you for catching that very goofy error that I made like 3 times in a row, even with the math in front of me. All right, well, take care and see you guys later.
Take care. Bye.
Bye-bye.